are some things that are outside of my control, for example, good Wi-Fi access. So just so you know, because I'm going to be doing stuff on Google Colab, and you can as well. The EduRoam Wi-Fi is not great in this room. It's great out there, but it's not great in here. I was testing it, so I would recommend that you connect your laptops to the free Wi-Fi of this building. That one seems to work okay. The second thing is I just want to get a sense of who in this room is willing and able to really take out your laptop, do some coding, learn it. It takes a bit of energy. Yeah, okay. A few, okay, that's actually more than I expected. So you guys are actually, great, nice. Okay, in that case, I have different versions of this talk. I have the one where I just talk a lot, which is fine, and you're gonna get the theoretical knowledge, but I think it's just better for everybody if you're really hands-on and actively working on it. The only problem with that is that if you're not, and you just kind of want to watch, then in the periods of time where people are working, you're gonna be a bit bored. That's the downside. Okay, so in that case, I'm gonna get going. So Neuromaps is a toolbox. This is a fun animation. A lot of the muscle behind the software is done by Ross Markello. How do I make it come back? Okay, I moved my mouse. It's all good. Ross Markello is a lot of the muscle behind this toolbox. He was a PhD student in the lab that I'm a current PhD student, and now he is making a lot of money in the Silicon Valley. And Vincent Bazinet is another big important figure. He's sitting right there with the pink cap. If you guys have questions as we're doing the hands-on demos, it'll be mostly, I can answer your questions too, but it'll be mostly him running around. Feel free to ask things. Don't feel like you're interrupting the whole workshop. You're not. We have 2 people. That way, if there's something that's going on, but you don't want the entire room to know that, something's going on, you can just flag Vince. Okay, so I like to start with this little analogy about what Neuromaps is. Let's just imagine that we're early day explorers of the Earth. And one of the first things you might want to know is where the continents are. And that's obviously important to know. It's kind of like knowing where the brain regions are, just knowing the general anatomy. But once you have this foundational map, you can start to annotate it with different information that you are interested in. So for example, if you're interested in energy consumption, you can annotate your map with a map of energy consumption. In terms of the brain, that could be metabolism. Where in the brain are there higher rates of metabolism? You might want to know where you're going to get a good cell signal. Those are supposed to be cell towers. So where in the brain, maybe there's the density of a specific receptor. Because if you think of a receptor, that's a little cell tower listening for a specific signal. Maybe you want to know where your text messages are going to be sent really quickly. This could be in the brain, places that are highly myelinated, so your signals are being sent quickly. And all of these maps are informative on their own, but when you start to overlay them on top of each other, let's add in connectivity, forestation, river systems, you get not only a more comprehensive idea of this thing, which is the world, or in our case, the brain, but you also start to get an idea of how these different things are working with one another. So what do we need to make this more comprehensive picture? We need the data, so we need all these different maps that we can place on top of each other. We need them to be represented in the same way, which is tricky, and actually the keynote was really awesome because it was kind of talking about a lot of the issues that we have, things being in different spaces, how do you compare them, how do you put them together? And we need good methods for making these statistical comparisons so we're not running around claiming things that might not actually be the case. So that's where Neuromaps comes in. More specifically, it is an open source Python toolbox. Don't worry if you're not a Python person. Maybe I'll just ask, how many people here are familiar with Python? Oh my gosh, it's gonna be easy. It is, but if you're not, don't worry, it'll be fine, because I'm gonna be doing it all in Google Colab and you'll be able to follow along. It is aimed at placing human neuroimaging data within the broader neuroscientific context. So really try to cross these disciplinary bridges and make links with fields that you might not be an expert in. So for example, I am not a geneticist, but I'm now able to make links with genetics data or genomics in general. And more specifically, it's there for accessing, transforming, and robustly comparing human brain maps. So here's the workflow. It's quite modular. You can take and leave what you like or don't like. By the end of this hands-on session, we are going to work with pretty much everything, and we're also going to have a theoretical knowledge of what it can do, but I'm really hoping it's not just going to be theoretical, you're also actually going to do it and get a sense of how it's done. So for the first part, if you want to be able to compare data, so for example, you have some map that you've collected in your lab, and you want to get a sense of what are the genetic or cellular or receptor architectures that might be underlying this maybe functional activation map or whatever map you happen to be looking at. You're going to need access to that data. So what we've done is we've compiled a bunch of different data sets and different brain maps or brain annotations, and we've made them available to you. So we have maps of metabolism. Now at the bottom, this is like a cheat sheet, but don't worry, you don't have to memorize it or write it down. This would be just like how you do this, how you're doing the thing that I'm showing. Metabolism maps, microstructural maps, functional maps. Let me take some more time. So metabolism like blood flow, blood volume, oxygen, glucose metabolism. Microstructure like T1, T2 ratio or cortical thickness. Function like intersubject variability and functional connectivity, the functional gradient. Expansion maps, this is over ontogeny or phylogeny, so how has the surface area of the brain expanded across development and evolution. Electrophysiological maps, these are coming from MEG. So these are different signatures of neural rhythms, including the intrinsic timescale. And finally, genomic maps, which can be worked in conjunction with Abogen. Abogen is a separate software toolbox. I'm not going to get into it unless you guys really want me to, but essentially it is there for working with Allen Brain Atlas data. So that's really spatially comprehensive gene expression in both the human and the mouse. There's also a whole receptor atlas in Neuromaps. This is work that I did last year or 2 years ago, and pretty much we collated a bunch of receptor maps for a lot of different receptor systems, and so this is nice because now you have these brain maps of where different receptors are. Very importantly, we have a contribution pipeline, so the data that's in Neuromaps is biased by two things. First of all, the history of neuroscience, just the things that we in this field are interested in and therefore are collecting, but also it is very much biased by the developers like myself. So if there's something that you feel that we've missed, absolutely let us know or contribute. It is trying to be very open. And also very importantly, if you do use Neuromaps data, we're not the ones that collected this or acquired the grant money to collect all this, so please cite the original contributors. That is very important. We have this master table, which I will show you how to get to, but essentially it tells you the data, the info, what you need to know, who you need to cite, what paper you can go to get all the nitpicky details if you want that. Okay, so that's the library. Now we are going to do some coding, and I'm going to keep going through each module. We're going to do this. We're going to do some coding. So here's what I want you guys to do. First of all, bring out your laptops. Nobody moved. That means that your laptops are all already out. And we're going to open up Google Colab. So I want to get a sense of okay, when you're done doing the thing that I need you to do, can you just look at me so I can get a sense of if people are, oh, was that a question or you're good? You're good. You're looking at me. Nice. Yeah, okay, so get yourself a Google Colab. That's just go to Google Drive, do the thing plus Google Docs or whatever, and instead of Google Docs, you go to the Google Colab part. This is going to be in Python. It needs internet access, but besides that, it should be all good. The first thing we're going to do is we're going to install Neuromaps. And you could just pip install Neuromaps, which is in Python usually how we install different packages. By the way, this is a good time for me to tell you, it is there on GitHub. This is what it looks like. NetNeurolab is the GitHub repository for just my lab in general, and not mean my supervisor's lab. It is there, and I merged a pull request about docs, very helpful. Yeah, so we have the documentation here, or just the GitHub page there. There's the documentation here. It's documented for all the different things. So this is where you should be going, the docs, when you're not sure how to do something. We're going to start with just installing Neuromaps, which I'm going to do with you, but for the rest, I'm going to try to get you guys to do it first, so you're not just copying me. That way you actually internalize it. Okay, so pip install. I'm going to install directly from GitHub just because it's the most updated version instead of installing the one that's on PyPy. So git plus, is this how you do it? github.com/netneurolab/neuromaps. Let's see if that works. Yeah, and when I code in front of people, I usually can't do anything, so this is going to be a struggle, but it seems to be doing something. Okay, so yeah, you guys are supposed to be doing this as well, and when you're done, you are going to look at me, so I have a sense of when to continue. Mm-hmm. Can you guys see the text? Should I make it bigger? Nice. How do I do it? Control plus. How do I make it bigger? Good. Is that good? Or should I make it even bigger? You good? Okay, great. Okay, are people looking at me? I still see some people working, so I'll give you a couple more seconds. Okay, we're good. Heads are up. So it's installed. Did anybody run into issues? Okay, so I mean, we're done. I could finish the workshop right here. You have it installed. You know how to access. You can see the docs. The rest is honestly just like you figure it out on your own. But I'm nice, so I guess I'll walk you through it. Where's my mouse? I'm just going to delete this output because it's annoying me. Okay. So what I want you to try to do, I'm not going to do it for you. You have to figure it out yourself. Go to the docs. Try to figure out. I just want you to list out what are the annotations or the brain maps that are available in Neuromaps. And I'm going to start with a little hint. Let's import Neuromaps. But maybe more specifically, I'm going to import from Neuromaps, import data sets. That's what it's called. So you'll see in the GitHub, this is what I personally do when I'm like not sure how to do things, which is most of the time. I go to the GitHub, I look at how it's organized. There's data sets right here. I'm going to import from data sets the data, but also just a sense of where the data is. I don't really want to give you all the answers, but if you go to user guide and you're like brain maps and annotations, how do we print out the annotation? I wonder. I'm just going to stand here for a bit. So try to figure out how to, let me go back to, try to figure out how to get a sense of how many annotations there are in your maps right now. And if you figured it out, raise your hand and tell me the answer. This is fun. I feel like a teacher. And if this is just totally confusing and you have no idea what I'm talking about, let me know as well. I can definitely guide you through more. Vince is just laughing the whole time. I can hear that, Vince.
78.
That sounds right. I had 73 in my head, but that sounds right. I mean, I trust you. You just did it. So nice. We have a number. Anybody else? You guys doing okay? You got the same. Nice. Easy peasy. So, okay, now let's see if I remember how to do it. So what it's like, datasets.available annotations, and then the length of this, right? How do I go? Yeah, nice. Okay, so we have a sense of how many there are. Now let's print every single one out. Okay, so this is what's there, and then what happens when you, so right now we haven't downloaded anything, but what happens when you download it, so when you use the function fetch annotation, that was another spoiler, I keep giving it away. Then it's going to be downloaded to your device. In this case, it's Google Colab, so it's being downloaded to like Google's temporary thingy, but if you do this on your own device, it's going to be downloaded into a folder on your device. You will have the data. So let's go and figure out how to print out the list of annotations. Hint, hint. Go away from that, so you have to find it yourself.
I have a question.
Yeah.
So the annotations, are they defined at the voxel level or at the mesh?
That is a great question. So the annotation, so feel free to keep working or listen, up to you. But the annotations are provided to you in the space in which they were made available the first time when they were published. And so what this means is that we try to do as little tinkering as possible to the data so that you have it in its like native form. So the data can be in different forms. It can be in a volumetric space, M9152. So that would be, yeah, volumes. It could be in surface space. We have FS average, FSLR, and Civit. And different densities. So FS average 164K, 32K, etc. And so what you'll notice if you manage to be able to print out the list of annotations is that the way that annotations are defined, let me print for annot in datasets.available annotations, oops, print annot. There we go, it worked. Okay, so what you'll see, every single line here is a different annotation, so a data set you could download, or not data set, but like a brain map. And the third item is the space in which it's defined. The fourth one is the density. Okay? So for example, this one, description, so the way it's organized, it's the source. By the way, this is trying to follow like BID style. So source, description, space, density. So here the source is Abogen, is actually the Allen Human Brain Atlas, but it was processed using Abogen, the toolbox. The description is it's gene PC1, the first principal component of gene expression. It is in FS average space, 10,000 vertices. Does that make sense? Yeah, we good? People are mostly looking up. So other stuff. Now, some of these sources can be a bit cryptic. What we try to do is we make the source the last name of the first author of the paper, and then the year of the paper. So for example, Belliveau 2017, that's a paper, Belliveau et al. 2017. They published a serotonin atlas. And because this is a bit overwhelming and confusing, a really important and handy hack I see Paul taking pictures, so I won't change yet. Okay, there you go. Is to go up to, if you just go to like regular old Neuromaps, you will find a big thing that's like, please cite original stuff, and then in our wiki at this link, there is a massive list. And this way, if you look at Belleville 2017, you're like, I don't know what AZ10419369 is. That's the tracer name, by the way. We didn't want to give the description the receptor name because there would be different receptors with different tracers, and that just gets confusing. So it's the tracer name that you use in the PET imaging protocol. But here is the handy description. It's a PET tracer binding image. It's a Bmax value, 2,5-HT1B. That's a serotonin receptor, 5-HT1B. Got it? So if you need the 5-HT1B receptor, you just look, what is the description? What is it filed under? What's the naming convention in Neuromaps? You have the info here. You have the number of people, age, and then very importantly, you have the papers to look at. So if you want the full methodological details, that's where you go. And here is where I printed out all the different stuff. And you can see how they're different. Good? How are we doing? Everyone? Nice. Okay. Awesome. Thanks for the thumbs up. Let's just download one real quick. Now pick anyone. Don't pick the one that I'm doing because that's not going to make it fun. But like, I'm going to let you do it, so no spoilers. So figure out how to download a map. You're going to want to save this as an item, so make it like cortical thickness equals the function for downloading the map, and then fetch that cortical thickness map. And the place to look, bingo. So here is where you can find, I'm giving away too many of the answers, I'm moving this. So how are we doing? Can some people, when you've downloaded something, can you let me know what you downloaded? Just like shout it out. Ooh, also, pro tip, you can put in all of the input parameters for fetching data. So the function is called fetch annotation, and it takes in 4 things. It takes in the source, the description, the space, the density. However, you do not need to provide all of that. If you just provide one of them, it'll just give you everything with that input parameter. Make sense? So for example, if you were to say, fetch me the data that's in FS average, it's just going to give you all the data we have in FS average space. That's maybe not the most useful, but on the flip side, you could say something like, I want to get HCP cortical thickness map. You say fetch HCP cortical thickness map. There's only one of those. That way you don't have to put in all the information. But of course, you can put in all the information. It can be found here. Here. So, anyone download anything yet? What'd you download?
Flumazenil.
Nice. Yeah. Flumazenil is GABA? GABA. Yes, I got it right. Anybody else? What did you download? Sorry?
I don't know how to pronounce it, but Tuominen.
Oh yeah, so that's the last, he's Finnish. That's why it's hard to pronounce. Anyways, that's the last name of the first author of the paper. That is that CB1, the cannabinoid? Or MOR, mu opioid receptor? Neither? Okay, let me check. Tuominen. FUBV, that's for VHCHD. So that's also a receptor. This is in M9-152 space. I have a question for the flumazenil amine. Hey. Yeah. Did you download the FS average or the M9-152 or both?
I said this equals flumazenil.
And that's it? Perfect. Okay, so let's just do what Amine did, just because this is a nice educational moment. So flumazenil.
Yeah, it has 3 space. Oh.
It has both probably. Okay, so this is what you guys were supposed to do. Fetch annotation is the name of the function. Of course, you could be fetching anything, so I'm just happening to, I don't know how to English. I'm getting the flumazenil, and so I'm going to say desk flumazenil. Now, and then let me just print out what it, yeah. So what happens if you just give it one thing is it's gonna download everything that matches that description. So if you are extremely specific and you give source, description, space, and density, it'll just download that one map. But if you're a bit more general and you just give it, for example, description flumazenil, it'll give you everything that is flumazenil. And in this case, here it is. So it's gonna give you a dictionary. And this is one of them, Ducart 2018 flumazenil. that is a MNI 150. This is where I downloaded it, by the way. So in this case, not so helpful because it's Google Collab, but if you're doing this on your local device, then you'll be able to find it in that folder structure on your computer. It is downloaded, you have the data. Here's another one, another flumazenil map. It's from a different source. So this is Norgard 2021. The other one was Ducart 2020 or 2018, something. This is MNI 152, and then there's a third one here, flumazenil, also from Norgard. This is an FS average, not an MNI 152. This one is important. The data that comes from Norgard and Billybo, I know this is kind of a detail, but when you download this, there's a little warning. It says data from Billybo 2017 and Norgard 2021 is best used in the provided FS average space. So pretty much they provide both the MNI 152 and the FS average. We have both. We recommend that you use the FS average. It is better unless you're specifically interested in subcortex or non-cortex, because of course surface data is only cortex. If this is confusing, this whole surface volume, whatever, I will get to that like right now. So have we all downloaded maps? You have something, other people is data, yes?
HCPS, from it.
Nice, which one?
All of them.
Nice, thorough, why not? So yeah, if you just want to download the one map, you can just be more specific in your query, or you can fetch them all. Okay, I'm gonna move on, we're good? Nice. Okay, I'm gonna go back to my slides. So at this point, this one. I should probably just close this one before that makes it confusing, whatever. Okay, so we have the data and we know how to fetch it, and this is actually true, you do know how to fetch it because you just did it. The problem is that we make it available in the original coordinate system, and so in its current form, if you download two different data maps from two different coordinate systems, you can't necessarily quantitatively compare them because they're in different spaces. Now, let me explain if that's confusing. It's a little bit like, so the analogy I like to give, or the one that I gave to my mom when I was explaining this, is that if I were to give you a map of like Fox density, but provided in the form of a globe, that's 3D, versus a map of force density, but provided in the form of a rolled up piece of paper, you can make qualitative judgments about whether those two maps look similar to one another because you know the landmarks of the world, of the Earth, right? But you can't make a quantitative judgment because they're in different spaces. And it's the same thing with the brain. You can provide it in volumetric space, you can provide it in 2D surface space, you can provide it in different densities of the surface space. It's like a total mess. And so if you want to make qualitative or quantitative judgments about whether these two maps are correlated, essentially if you want to do like a Pearson correlation of A comma B, where A and B are two different data maps, you need to put them in the same space, okay? And so what Neuromaps does is we do provide these transformations between four really common spaces, specifically MNI 152, that's volume, to three different surface spaces, FS average, FSLR, civet. And then within that, different densities. So just to give you an example, let's say you have a map like a cortical thinning map or in general a thinning map in MNI 152 space. You want to compare this, because you're looking at it and you're saying, I want to know what the signatures of this are in terms of cortical thickness, in terms of T1, T2 ratio, in terms of gene expression, in terms of this is developmental expansion across the lifespan. But the problem is some of these are in FSLR space. There's 32,000 vertices, so your vector is 32,000 of length, 32,000. Other things are in FS average, that's 10,000 vertices. Some things are in civet, that's 41,000 vertices. So what we do when we use registration fusion, that's what we do to map from volume to surface, so specifically MNI 152 to civet, FSLR, or FS average. What you're doing here is you're tracing out of the group average, what does my cortex look like? Map your native, or subject's native T1 space to MNI 152 space, then T1 space to FS average space. So you're going from native to these two different surfaces, MNI 152 or FS average, and then if you concatenate those two mappings, because it's just a linear combination, you can go from MNI 152 to FS average. So we didn't make this up, by the way. We did not make up registration fusion. It was originally kind of proposed and then implemented for one specific transformation from MNI 152 to FS average 164K, and then we applied it for the rest of the transformations. Okay, so that's registration fusion. That goes from volume to surface. There's also going from surface to surface, and here you can see all the different densities we work with. So for example, FS average is not just FS average because we can't have things that are simple. So of course there's 10,000 vertices, there's 41,000 vertices, there's 164 vertices. I think there's probably 4 vertices, 32 vertices, yeah, whatever, right? So there's a bunch of different ways that you can store your data, and if they're in different spaces, you're not going to be able to compare them to each other, so we have to be able to transform. We use multimodal surface matching to go from surface to surface. For example, if you want to go from FS average to FSLR, you would take the sulcal depth map of one space, like FS average. So this is not data, right? This is just how deep is the brain in different points. the cycle depth map of your other space. So here, FS average, do you see my mouse? Yeah, FS average over here, FSLR over here. We're going to project these onto the sphere. This is something that people love to do in the cortex. It's sort of sphere-ish shaped, not really, but sort of. So we project things, and that just makes things easier because now it is very uniform. And then you can tell we want to align these two spheres, and you can actually see where they should be aligned. You have this situation over here. This is a cycle depth, right? So this is demonstrating how the brain is folding, and so it's kind of a representation of the brain on the sphere. And you want to match that with this guy, so you're going to rotate him, get them to align, and now you have a mapping of how to go from one sphere to another so that you can go from one brain to another. Which is actually very cool. It's a very good idea. This is Emma Robinson. She did this in 2014 and then expanded on it since. Then we can apply actual data to it. So for example, here's the GABA A receptor density. I think this is actually flumazenil, the one that Amin downloaded. So it's kind of like, that's how it works. Like if you were to transform it, you have it in FS average space. If you wanted an FSLR space, you're going to use that mapping between spheres that we can generate from FS average to FSLR, spin around your sphere, and then project it back to the FSLR brain, and then now you have this data in that space. Now you can tell they're not identical because they're not identical brains, right? These are different brain templates, so there are going to be changes. It's always best to work with, the original space that you have, but they're also pretty good. And in general, one analysis we did for this Neuromaps project and the paper that came out of it was we transformed the data, like all the data we had, into a bunch of different spaces, and we correlated them. And we said, how much does the correlation coefficient change, and how much does the p-value change? And the answer was very, very, very little. It made really little difference when we were transforming. Okay, so that's all the transforms going from volume to surface or surface to surface. Oh, this is exactly what I was mentioning about if you take all the data, you make a similarity matrix, so you have like 20 maps here, you're correlating them, and you're doing this in different spaces. The change in the correlation coefficient is very small. It changes by a maximum 0.05. That's what this is showing. And here's one example where the p-value does change. It goes from significant to non-significant, but your significant one was 0.049, so it's kind of sus to start. Yeah?
So one question real quick. How did you know what space the map was in? Does it come with an annotation that says it's an FSL space?
Yes, that is a great question. So when you download the map, the way that the file name is defined, here, it tells you the source. It came from Ducart et al. 2018. The description is a flumazenil map. The space is MNI152, so that's the space. This would be volumetric. And in this case, the resolution, 3 millimeter, 2 millimeter, 1 millimeter. If it's surface space, it would tell you 164K, 10K, et cetera, et cetera. Another place, so that's just in the file name, which makes it easy. That way, when you download it, you have it right there. But actually, the way that Neuromaps data in general is named is with this convention of source, description, space, resolution/density. So even when you're looking for data, let's say you only want the FS average data, you could just fetch the FS average data, and that works as well. And this table is in the wiki, which used to be really hard to find, but now there are like links everywhere pointing you to it, so hopefully it is no longer hard to find. Okay, so I think this is actually time for the coding session part 2. Oh yeah, last thing, we parse-laid. So I personally work almost entirely, actually not almost, I work entirely at the parse-lated level. I have never really worked with the vertices or voxel level data, even though I'm here like talking about it. So we do also parse-late. Given the parselation that you want to work with, defined in whatever space you want to work with, you just provide us with that file, and then we will take the FS average data or the FSLR data or whatever, and then spit it out in, for example, Desikan-Kiliani 68 nodes, or Schaefer 400 nodes, or whatever else people are working with. Okay, let's code. So,
One question.
yes.
Do you also implement transformation to the BigBrain space?
So that you can use BigBrain Warp. So Casey Piccola, I can just show you. I'm here. This toolbox will go from the BigBrain space to FS average, FSLR, or Civit. We thought about including it, but then we were kind of like, well, Casey did it, and we don't want to just like wrap what Casey did, you know what I mean? Like it sort of felt like a bit redundant, I guess. But we might still add it because there's a lot of cool BigBrain data that's not in here right now, but we were thinking of adding it. So essentially, what she did, she's actually already has all the BigBrain data in these common coordinate systems like FS average, FSLR, Civit. I actually don't know if she has Civit, but definitely FS average, FSLR, and I think MNI152 too as well. So you can get the BigBrain data in those spaces and then compare them to the data in Neuromaps, or what you can do is you can take the data in Neuromaps, transform it to BigBrain space using BigBrain Warp to be able to make these comparisons. Does that make sense? Yeah, I agree, but don't you think, like, okay, I agree, but I also, like, felt I didn't want to just, like, take the thing she did and then put it in the toolbox and give it its own, you know what I mean? Like, I felt a little bit like it's taking her.
You can just provide the bridge, right?
That's true. Or at least, like, link it and make it really clear.
I mean, I tried
Yeah.
using this and it felt a bit more complex than just calling a Python.
Then just like MNI 152 to FS average, yeah, that's true, absolutely. And the transforms are there and they're very useful, so that's a good point. Yeah. Okay, are we ready to code? How are you guys doing? I'm not even gonna like wait for response. We're gonna get right into it. Okay, so what we're gonna do is we're gonna transform the map that you just downloaded. So I don't know what space you downloaded it in, and some of you downloaded multiple, so pick one. So you could just index that. Like for example, with flumazenil, you could say, let's just take flumazenil bracket 1, or 0, because it's Python. And then what I'm gonna get you to do is I want you to transform it to a different space. I don't really care which other space you transform it to, just I want it to be different. And I'm gonna kind of give you a bit of a caveat, which is that Neuromaps by default, but also just general good practice, is to always downsample. So that's easy if you're in volumetric space, because the volume is always gonna have way more data points than any surface. That way, if you transform to surface, you're always bringing it down. But if you're in surface space, if you're at 10,000, don't transform to 164,000, because then you're upsampling data. You're gonna be imputing a lot. Let's, you know, in general, when you want to compare data, you always want to compare it in the most coarse resolution possible. And in this case, what you want to do, Neuromaps import, transforms. This is what you want, the module that you want to be importing, transforms, and then from transforms, you can find the functions that you need. And when you're done, you will look up. And don't forget, if you have questions, do let me know. I'm going to start transforming it. So if you're noticing, I'm trying to do the same thing right now, and then I forgot what the parameters were, so I'm looking it up. So this is very normal. You're not expected to memorize all the functions.
I have a question on you. I've tried a number of different transformations, and I keep getting a subprocess error, failing with non-zero exit status 127.
That is, I don't know what that's referring to. Vince, can I throw you up there?
Basically it's saying WB not found.
Oh. Oh no.
You should try it because I think it's really doable more than
Okay, so pretty much one thing with Neuromaps is when you download it, is also downloading WB command, which is like the HCP transform. It's because it's using that under the hood. But when I did this before, it worked. Let me just see what's going on. Transforms, oops. So everyone's getting the W command issue? Darn, what is going on? Okay. Yeah, me too. Wait, never mind, not me too. Mm-hmm. Hmm. Okay, this is my cheat sheet. 1 second. Let me just make sure. Let's see if it works here. If you guys have Python installed, you can try using it there. It should be fine. Like the installation with the WB command is probably a Google Colab thing where it's not fetching the. But it's a bit odd because I did this workshop before and it was fine. So I don't need to run that. Sorry guys, 1 second. Wait, why did this work? What's the difference? Pip install good plus. What in the world? So everyone got the issue. Nobody got the transfer. Did you get the transform to work?
I picked a different transformation.
And it worked?
Yeah, it did. And
So it's
from MNI to FSLR. It's fine, but I did different.
interesting. Yeah, makes sense. Okay, so there's something weird with the. You were doing surface to surface, right? FS average to FSLR, or FSLR to FS average.
No, it's just MNI to.
Yeah, sorry, I meant
Yeah, I got the error for SLR to FS average.
Oh wait, but isn't your data? Wasn't your
I
map?
chose a different one.
Oh, okay, makes sense. That's odd. Can you guys try doing a different transformation, see if that works? So here's from, and Vince, I'm assuming you're on it, figuring out what's going on. Yeah, nice. Vince is on it, guys. Yeah, it's a collapse thing. It's about like getting workbench command like installed properly and making sure the Neuromaps can fetch it, like can access it. I don't know of anybody that's had issues when doing this on their local device. Yeah. Same issue?
Yeah.
Even with a different transform? Even if you go from volume to surface, but you have to make sure that your data set is volumetric first.
Which transform did it work?
Yeah, which transform, was the issue from FS average to FSLR?
SLR to FS average.
FSLR to FS average.
The inverse from
And the inverse. Okay, but did you get it to work from MNI 150, from volume to surface? Give it a shot. But don't forget, like if you're doing a transform from MNI 152 to FS average, your data needs to be in MNI 152 for, you know what I mean? You can't just give like an FS average data and like say MNI. How are we doing, guys? You know what? Why am I telling you guys to do it? I can do it myself as well. Let's see. Okay, so there's something with surface. Workbench command, like yeah, there's something going on. If you want, if you're feeling really like ambitious, you can try to do it locally instead of using Google Colab. So like if you already have Python installed and all this kind of stuff, just install it onto your local device, download it, try to do the transformation. It should be fine. If it's not.
I'm doing it locally and now it doesn't work.
Are you serious?
Which one? The FSLR to FS average.
Okay, Vince is on it. Okay, you're on it? Cool. Maybe it's a version thing? Well, in any case, this is a good time for me to say, wait, let me get to Neuromaps. If you find an issue or a bug, we have an issues thing. So you can be, oh, no, this is something else. It's an enhancement. Never mind, sorry. Yeah, so you can have like suggestions. You can, if you're having an issue, general questions too. We're pretty responsive. In fact, you can see like, you know, things have been commented on. Yeah. Okay, so Vince is on this transformation issue. That is odd. It's not been like that before, but Vince looks like he's having a great time right now because he loves debugging. Look at him. Look at that big smile. Sorry. Just kidding. So what I'll do, is anybody like actively coding right now, or are you just kind of like confused? Generally confused, I feel like is the vibe. Anyone actively coding? Okay, so what I'm gonna do is I'm gonna continue with the presentation. Vince is gonna figure out what's going on with the surface transforms, yeah?
Maybe a quick question.
Yeah.
Why is there FSLR to FSLR, FSLR to FSLR?
Yeah, that is for resampling. So if you wanna go from 32K to 10K or 4K or whatever, that's where it comes in. Technically, resampling is not a transformation, but we just put them all under the transforms module. It's like a transformation within the same space. Same thing with M&I, you can also do that, like go from 3 millimeters to 1 millimeter, that sort of thing. Yeah.
No, exactly. It's more.
Oh, and if you guys have, actually, if you're just kind of stuck but you want to try something else, what I recommend is try to figure out if you can parcelate your data. How's it going? Do we have a solution? Oh yeah, please tell me.
That to do these things, we have to have the connector workbench installed.
Yeah, but Collab should do that by itself when you install Neuromaps. Yeah, when you pip install, Collab should also fetch workbench command.
Well, if it doesn't work locally, that's why. So you need to have the connector workbench installed locally in the computer, because like on the Earth, all the transformation are using
Okay,
the
let's-
connector workbench.
Yeah,
Let's-
so the bit install doesn't do that.
It should do that. Like that should be, but let's just make sure. Maybe if it's like not available on your path or something like that.
I'm not sure it installs it.
I've honestly never like separately gone to.
No, it can do us.
Yeah, it does.
During the pip install, like if there's, I don't know.
In the documentation, it explicitly states that you must have the connected workbench installed.
Yeah.
Accessible in the computer.
Yeah, but usually, so you definitely need to have the Connect and Workbench installed, but usually it should happen directly through the pip. It might be because I'm not directly downloading from PyPy, instead I'm getting it from GitHub. Maybe that's why. Like if you just do, like you did pip install Neuromaps? You didn't get, okay, weird. Well, in any case, if you have the issue, we have the link right here in the documentations, like you have to have Connect and Workbench installed, and all you do is download now. It's actually simplest setup. You just need to make sure it's on your path, but it should be like that automatically. What's up?
No, I just double checked.
Okay. It would be great if we could have one person get it to work out.
I made it work.
Okay, Vince, do you want to help? Anybody else want like direct kind of Vince tutorial help for getting Workbench installed, making sure that your transformations will be okay? If so, just yell at him. Or yell at me, I'll yell at him. Okay, what I'm going to do in the meantime is just let you know that we do, okay, so we parselate, which I mentioned before, and so I want you guys to try to parselate the data that you have. So for example, if you have one M&I 152, so first of all, if you don't work with parselated data, you can ignore this because whatever. But if you do, so for example, if you work in Desk and Kiliani, you should have a file that defines at a specific space. So for example, M&I 152. For every voxel, it's going to map which parcel does that voxel belong to. So it's going to be mapping of the numbers 1 to 68 if you have 68 nodes. All these voxels that have the label 1 on it are pointing to the parcel 1. They're going to get averaged together in your map. You're going to have some parcel in the end. Make sense? And that's just how parcelations work. So if you want to parcelate your data, what you can do is you get that parcellation file, which if you're working with a like really specific parcellation, that's something that the team develops themselves. Like when you put out a parcellation, that's part of putting out a parcellation. In fact, I can give you an example. Thomas Yo's group put out Schaefer 400 a couple years ago, or Schaefer in general. Thomas Yo, Schaefer, yeah, there. And they have it on their GitHub. The Schaefer parcellation in different spaces, so you can see, get the parcellation file, if you want it in M&I 150 or M&I space, if you want it in, this would be FSLR space, etc. So this is the file that is labeling for every vertex or voxel what parcel does it belong to, and what you need to do for Neuromaps is you just need to provide that file, and then it does the parcellation. So let me just do an example. I'm gonna get my parcellation from NetNeuroTools, but you can get it from wherever. NetNeuroTools is just like our lab open kind of functions that are handy to use. So from netneurotools.datasets import. You know, I take this back. I'm going to do something easier. I think Nylearn has a fetch Schaefer thing, right? If you guys don't know, Nylearn is like a really popular Python neuroimaging. It does, right? What's it called? Fetch Schaefer. Let's see, Nylearn. There, fetch Atlas Schaefer 2018. So that's what I'm going to do. Schaefer. Oops. And this is probably a bit more informative if you do it with the parcellation you actually care about and use yourself. I'm just going to do it for this one because I've used this one. Oh, I typed something wrong. From nylearn.datasets. Bingo, and then and this is in what space? 400, that's good. So once you have the parcellation file of your choice, in my case, I'm getting Schaefer, and it has a list of all the different parcels. It's 400 of them. Actually, I think this is going to list literally everything, yeah. Then, okay, by the way, don't look at the screen if you want to do this yourself, and it's usually more informative if you do yourself, because that way you like internalize what you're learning. There's a new module, it's called Parcellator. Let's see how Parcellator works. Can I get a show of hands, who here is actively trying to parcellate? Who's doing the parcellation task? Okay, a couple people. Who here does not work with parcellated data? Okay, people work with parcellated data. Okay, well, I encourage you to try. Since there are a few of you, we're gonna keep at it. So what Neuromaps does is it takes this parcellator, you give it the parcellation file, and you tell it what space it's in. So for example, you give it the Schaefer 400 parcellation in M9-152 space, you tell it it's an M9-152 space, and then you can give it whatever map you want, you tell it to transform into that parcellation, and it will. So because this is an M9-152, I need data in M9-152. Let's take Flumazdil. I think I already have it actually. And then the way you parcellate is you just say your parcellator that you defined, and it's fit transform is the function. So in this case, let's see. Just M&I maybe? Let me check.
Justine,
Mm-hmm.
you have to do it's a dictionary and has a key maps. Schaefer.
Oh.
Yeah.
Oh my gosh, true. Thank you. Thank you. Haha, that's so great about doing this in front of everybody. Why am I still getting an error? This path should be string. Flumaz. Oh, is my flumazenil currently? Wait. Print. Flumazenil. So as you can see with the parsellator, it does. Oh, it's empty. Flumazenil. Norgard 2021 M&I. There we go. Okay, so now I actually got data before I was not getting any data. This should be fine. Oh, this is a string right now, so we need to load it. Ugh. Sorry, this is not really important. It's just I want to show you that the shape changed. And right now flumazenil is a string because it's a file in your computer. So I'm just gonna put nibable as nib.load. Flumazenil. Now this should be okay. Oh wait, actually, no, it's not gonna be okay. Ag data. Where's it get f data? Get f data? So this is like how I code in real time. I just try a bunch of things and then see which one works. This one, right? Sorry, what?
You're calling the image with a different name.
Oh. Guys. Get f data. Okay. This is an MNI 152 space. Is it get f data or is it ag data? Do you remember? Does anybody know? I'll just try both. Let's see what happens. There we go. Okay. So this, okay, for those of you guys who just watched me embarrass myself, pretty much what I did was I downloaded the data. Neuromaps gives you the string to where it's downloaded on your computer, so you can't just do it as a shape. You would need to load in the data, get the array. So I did load in the data and get the array using nibable, which is usually not something you would need to be able to do, but because I want to show you the shape of this thing, I went through that. And you can see my volumetric image is volumetric, 182 by 218 by 182. That is a matrix, right? So it's volumetric. It's a representation of the brain in the volume. Then I parsellated it. I said park fit transform. I gave it so park is the Neuromaps parsellator object. It has the space of the data, or it has the parcellation that I'm using in 152, in MNI space. So my data is in MNI space, which means my parcellation has to be in MNI space. And the parcellation I gave it is for Schaefer 400, and so it's going to spit out my image as a 400 length, a vector of length 400. So now you have the data that used to be a volumetric massive thing. It's now in Schaefer 400. If you do your analyses in Schaefer 400, you can just keep this, do your thing. And what I've done before, and what probably was more helpful for you, is to take this, to loop through, let's say you want a bunch of different data in Neuromaps, you loop through, you download a bunch of different data from Neuromaps, you parcellate all that to Schaefer 400, and then you have yourself a bunch of data in Schaefer 400 or whatever parcellation you want to use, and you can take your map that's in that space and just do a mass, well, depending on what your analysis is, but now you have them all in the same space, you can work with it like that. Questions? How are we doing?
I have a comment though.
Oh yeah, go ahead.
Also, what's cool about that is that here, she has a MNI 152 parcellation, and she wants to parcellate a map that's already in MNI 152, which is boring. But actually, if you have some random map in FS average at SLR that is not parcellated, and you have this parcellation in MNI 152, you don't have to do the transformation by yourself. You'll just say park at fit transform, and then you specify the map that you want to parcellate, and you specify the coordinate system of the actual map. It doesn't have to be the same as the actual parcellation, and it's going to do the transformation that you want it to do.
Yeah.
So it saves you a lot of time and a lot of thinking about what's actually what you want to do.
So for example, if you have a map in FS average, you can have your parcellation in FSLR, make your parcellation, this is a thing in FSLR, but then say I want to fit transform this from FS average, right? I'm just in the mic just because there's something.
Yeah.
And then you have your FSLR map, you have your parcellation FS average. It's going to parcellate it, but what it's going to do under the hood is it's going to transform that FS average to FSLR, just like you just did, except some of you did not do it because it did not work, but you get the idea. And then you get your parcellation, your parcellated map in 400 parcels, or 68 Descantiliani, or, you know, I've done this for the brainstem, so I mean, I'm actually talking about that on Friday, shameless plug. I parcellated to 58 nuclei in the brainstem. I mean, you can't do that with surface data because that's cortex only, but for volume data, if it's there in the subcortex, then you can certainly parcellate it to subcortical structures. Okay, I'm going to move on. There's like one last module that I have not talked about. So at this point, we have access to a bunch of data. We can transform them to each other's space. We can make quantitative judgments. You could do like a correlation coefficient, I don't know, like Pearson's R. You get your parametric p-value, you walk away, you're happy, you're done. And that is the case. You could just do that, but Neuromaps does also implement spatial nulls, which is what we recommend that you use when you're doing comparisons between brains, because when you do the typical brain analysis, or when you do a typical statistical analysis, that is assuming that your observations are independent. So in whatever statistical model you're using, it's assuming that observations are independent. In the case of brains, when you're comparing brains to each other, so for example, when you're correlating brains to each other, the observations are brain regions. And so the assumption for these naive statistical models, for example, your parametric p-value, when you just do Pearson's R, is that your brain regions are independent from one another. Now, of course, brain regions are not independent from one another in many ways, but in one way that happens to be important and kind of show up all the time is simply distance, because your brain is embedded, is a spatial thing, it's embedded in your brain, in your head. The relationship between two brain regions that are close to each other versus two brain regions that are far apart is inherently different, right? You have two brain regions that are close, that's one relationship, and two brain regions that are far, that's a different relationship. So they're not independent, and so we can't assume independence when we do our statistical models. So what we do instead is we apply these spatial null models that take this into account. So let me just give you an example. Here is random data, like literally simulated just random. And as you tune the spatial autocorrelation, as you increase the degree of, I guess you could think of it as smoothness in the brain, or just in general how similar you are to your neighbors, as you tune these more and more, you end up with two brain maps that are originally totally random and correlated at 0, but now are very highly correlated simply because of their smoothness or their spatial autocorrelation. And if you looked at brain data, you know that loss of brain data is on the smoother end. But even if it wasn't like, even if it's not smooth because of smoothing, it could also just be the fact that because you're in the brain, and kind of just the fact of the brain, not just the brain, but many things, is that when you're close together, you tend to be more similar than when you're far apart. We good? So what we do, oh yeah, this is a little bit like, so in my first analogy about the brain, about the Earth, this is like if I were to tell you that all of these maps are really correlated to one another because they all exist on the continents and not in the ocean. And that is true, but not particularly helpful or informative. Right? So if like you say, oh, these things are all related to one another because they're all representations of the brain, sure, that's true, but that's not very informative. It's not going to tell me, I want to know what is their relationship above and beyond the fact that they're both contained in space, that they're both brain features. Okay, so how we do this is we use permutation testing. So essentially what you do is you correlate your two brain maps, X and Y. You have some correlation coefficient. Then you generate a bunch of null maps of one of those maps. So let's say you're correlating X and Y. You're going to take your Y map and you're just going to shuffle it. You're going to use the spatial null model. I'll explain how it works, but for now, just bear with me. You're going to use that spatial null model, make a bunch of bogus maps or null maps, compute your correlation coefficient with all those null maps. That's going to give you a distribution of null correlations. You have your empirical correlation, you have distribution of null correlations, and so you're going to get a sense of whether or not your correlation is statistically significant. In other words, is it bigger than the nulls more than 95% of the time? And usually two-tailed, so you have to take absolute value into account. Make sense? So how we do that, this is empirical data. Naive models, again, that would be something like the parametric p-value or just shuffling brain regions randomly. That assumes that your brain regions are independent from one another, which is not the case in the brain. So we need to use spatial null models, spatial permutation models is one example, also called the spin test. And what we do here is we take our brain, we project it to the sphere again, using the same thing we did for the multimodal surface matching when we were doing transforms from surface to surface, spin that sphere around, and then project it back onto the brain. And so you can see, you have data here, you have projected it to the sphere, you've spun it around, and you've plopped it back down on the brain, and you can see that your neighbors are the same. You have retained the same spatial autocorrelation. You have retained the same kind of spatial topography, but it's a null map. This is no longer the same map as before. Make sense? And then another version is using parameterized data models, where instead of projecting to the sphere and spinning it, you're going to use a generative model to make a surrogate data. So you're going to estimate the spatial correlation of your data. You're going to make surrogate or fake data. Do the same thing, correlate your null p-values, get your distribution, calculate your family-wise error rate. Parameterized data models are nice because, well, they're not nice because they take a lot more time, but they're also nice because they can be extended beyond the cortex. The whole projecting to sphere thing only works in the cortex. So if you're looking at the subcortex, it's not going to work for you. Okay, and that we implement a bunch of different versions of spatial null models. These are all different versions. So there's like different ways of handling the medial wall, different ways of handling different parcellations, different ways of generating data, and then parameterized models. Which one to use where is covered really nicely in this Markello and Messick 2021 paper. The title is literally like comparing spatial null models, so it gives you a sense of which one you should be using in your case. Naive models, again, not recommended because they give inflated p-values. They're assuming brain regions are independent, which they are not. These spin tests only work for surfaces, so that's only cortex data. Parameterized works for volumes and surfaces, but can take a lot longer. And then depending on which one it is, there's like when you spin the data and then you plop it back down onto the brain, there's different ways that you can plop that data back down onto the brain, and in some ways you can say what is the closest brain parcel, and in that case you might have duplicates if you have a parcel that's kind of, or if you have a brain region on your spun sphere that's equally close to two different parcels, you might have duplicates in your brain, whereas in other cases you make sure that every brain region shows up exactly once in the null version. These are just formalities and technicalities. Whether or not the medial wall can move into the map. So you see this like gray business. Like imagine, we're doing this for one hemisphere at a time, right? So if you have the left hemisphere, big chunk of that is medial wall, which is we're not looking at. That's all grayed out. So when you project it to the sphere and spin it, you're going to have a big chunk of that sphere is medial wall. And so it might end up in brain areas like here. And so you'll just have to ignore those. You'll have to do your correlation or your null comparison, but just ignoring the regions that are now nans. Or you can do the versions that don't do that make sure that the medial wall is completely removed. Whether or not it works for parcellated and vertex level data or only for parcellated data, that also is how these are different from one another. And parameterized data models, in theory, work for anything parcellated, vertex, voxel, but in practice, if you're going to do this on a volume, which is a lot of data points, that is going to take ages and a ton of space. It is not recommended. So if you want to do parameterized models, I highly recommend that you're working at the either surface level or at the parcellated level, or you have access to like a lot of space and computational power. Okay, so that is the workflow. We have the library, we have the transformations, we now have the spatial nulls, and so you can do this enrichment analysis. Now before I go into the whole enrichment thing, let's try to do this null, which is usually the trickiest part. So I'm going to invite you to get your laptops back out. The module is from Neuromaps, import nulls. And I think, okay, if you parcellated something, I highly recommend you do it, well, I think it's better if you do it on the parcellated version, it'll just be faster. Don't do it on the volume. If you have a volumetric map, transform it to the surface, which we know works. So transform it to FS average, FSLR, and then do the null on the surface FS average or FSLR, okay? Or civet, like any of the surfaces. So does everybody here have a map that is either parcellated or in surface space? Or rephrase that. Raise your hand if your data, if you only have a map that's an M9152. Okay, great. So that means everybody has something they can build their null off of, where you're gonna, I'm not gonna do it, or I'm gonna try to restrain myself. Spatial nulls is where to look in the docs. If you're working with non-parcellated versus if you're working with parcellated, that, I mean, changes things slightly, but it depends on your case. You can be ambitious and go for the volumetric, but I would recommend, for now, sticking with the parcellated or the surface. And yeah, look up when you are done. Or if you need help, let me know. And okay, so there's a bunch of different nulls that you can use. If I actually just go here, reference API, go to the nulls. As you can see, each of these is a different function. You can use Alexander Bloch, you can use Vasquez Rodriguez. Feel free to use whichever one you want. I'm going to use Alexander Bloch. At the end of the day, it's pretty similar. But you can use whichever. And it should work. And just a reminder, when you do these nulls, what you're going to want is you're going to want to take your map and you're going to want to spin it. And you can spin it once just to make sure that you can do that. But if you're actually using this in a statistical test, you're going to want 1,000, maybe 10,000 versions of that spun map so that you can calculate the null correlation coefficient or whatever analysis you're conducting and compare it to that distribution, right? So if you want a distribution, you're going to need 1,000 plus of those rotations. I'm going to do 100 just for the sake of time. It's not going to take long, or it shouldn't take long. We'll see how it goes. But yeah, just to know. So you can do it for just one spin and just make sure that you know how to spin something, but or how to make that null. But theoretically, in your analysis, you should be making 1,000 plus. Okay. And generally recommend to use seeds in your work, because if you use a seed, then you can repeat it again. Like, these spins are all randomized, right? So if you use a seed, then you can reproduce what you've done instead of having it random each time. How are people doing? Anybody stuck? Yeah, what's up?
Quick side question. Is there a preferred viewer for surface data in a notebook?
Is there sorry, what?
A preferred viewer for surface data in a notebook?
Okay, so like plotting. You mean like plotting a brain map? So Neuromaps, I would not recommend Neuromaps for plotting because we do have a plotting thing in the Neuromaps.plotting function module. So it would be from Neuromaps import plotting, or from Neuromaps.plotting import plot surf template is I think what it's called, function. All we're doing is we're wrapping Nylearn. Nylearn's like plotting, and it does make a brain map, and you can see it, and it's not bad, it's fine. But if you want like a nice publication ready figure, people I know that have used a surf plot, that's pretty nice. I use the NeuroTools. Yeah, what's up?
I would recommend to use Brain Browser.
Brain Browser, okay. I haven't used that, but I will look that up. That really looks good. But yeah, I don't know, just making nice brain plots is kind of also a personal aesthetic kind of choice. So. Yeah, so we have it there for completeness because we're like, well, you're working with brain data, you probably want to be able to look at it, but it's definitely not the focus of Neuromaps. Brain Browser, that's cool though, I'll look that up. Let's see if this works. So I'm currently running my null. It's taking a bit of time. I'm making 100 rotations. And I have a few pro tips about this. If you guys get it to work. Did it work?
Yeah, very good.
Huh?
Yeah.
Nice. Very fast, is that what you said? How many rotations?
Maybe 100 rotations.
How many parcels or vertices? Which space? How many? Do you know? 10K? If you just print out the name of your downloaded map, it'll be in the file name. It'll say like space fsaverage and then den, den for density. Yeah, it's faster the fewer. I mean, if you imagine like you're taking your data, projecting it, spinning it, so the more data points you have, the longer it's going to take. That's why for the volume it is a pain because it's massive. At the parcelated level, it's quite fast. Oh, look, I did 32K was not bad at all. It's done. So you can see I have my map. Oh, by the way, if you're wondering why is it 64,000 vertices when it's called 32K, it's per hemisphere. So I have my map that's almost 65,000 vertices long, but I now have 100 versions of it. Each column is a different rotated map. It has been spun around. So if I have my original map, I can correlate it with each of these null versions 100 times. I'm going to get a null distribution of the null correlation coefficients, 100 of those. I do recommend you do more than 100, at least 1,000, I would say. And then you can calculate your p-value, which we do actually do for you. It's called, I'm not going to get into it just because I'm running out of time, but it's called compare images under neuromaps.stats. Yeah, compare images. We have a function that kind of does it all for you. So I showed you how to do all these things like individually, but you could just use compare images, give it the source, give it the target. It's going to do the transformation under the hood. If you give it the nulls, it'll use those nulls, and then it's going to spit out your correlation coefficient and your p-value, or whatever metric. It doesn't have to be correlation. It could be cosine similarity. It could be some other thing that you've defined. So who's gotten the nulls to? So you got it to work. How many did you make? 100?
The reason that was fast was that the density in the spinner was 10K.
That makes sense, yeah. But how many did you end up rotating? Just one, or?
No, 100.
100, okay. Anybody else? You guys managed to rotate? I'll give you more time. Remember, if you look up, that means that you're either done or you've kind of given up and don't want to work on it anymore, which is fair. That would be me, probably. And so just like in the interest of time, what I'll do is I'll kind of, this is my cheat sheet, show you an example. If you were to plot, if you were to compute a correlation coefficient between two maps that you've transformed to the same space, and you get some correlation coefficient 0.6, then you plot the null correlation coefficient between the same two maps, but you've rotated one of them a bunch of times. So this distribution is representing 1,000 data points. Every data point is a correlation coefficient between your original map and a null map. You're going to get a sense of whether or not your correlation coefficient is statistically significant above and beyond the effects of spatial autocorrelation. In this case, it does great. Your correlation is way above the null. But in other cases, your correlation rate might be right in the middle, and then you know that the effects are probably due to spatial autocorrelation, and this is probably not something you should take further. Or at any rate, you should understand that there are distance effects that are at play there. Anybody else? Nulls? Anyone? Did you guys get the nulls to work? If you're stuck and need help, do let us know. The idea here is that you can do these spinning. Okay, looks like we're good. Okay, nice. So just to wrap up, at this point, you have what you can create for every single map is this kind of enrichment plot of some sort of similarity measure between your data, your user map, and all the different data in the library. And you can get a sense of how your map is enriched. Is it enriched for specific cellular properties? Is it enriched for specific microarchitectural properties? Is it enriched for specific functional properties? And that's sort of like a way for you to continue your analysis and explore different hypotheses. If you see a big hit in the genetics, and you could take that direction and try to analyze that further. Just to give you an example, here's an analysis where I'm looking at different disorder profiles coming from the Enigma Consortium and comparing that to receptor densities. And this is like a nice time to just make a bit of a point, which is that just because Neuromaps has a bunch of data does not mean that you have to use it all. You can have a hypothesis. You can come in with a specific hypothesis about a specific data map and go in and use that. In this case, it was specifically about receptors. So the hypothesis was about how are different receptor densities shaping the progression of different disorders and conditions. And so this is a mapping between these receptors and diseases. And I'm not going to go into the analysis, but it just kind of shows you the power of being able to have access to all these different maps and representations. Yeah, so Neuromaps is out there. You can already do that. I don't even need to tell you this because you have done it. Again, big shout out to Ross. It is published, so you can read the nitty-gritty details. There's also a really nice commentary that makes you feel really good about data science in general and in neuroscience. I don't know. I thought it was really exciting when I read it. And I'm just going to quickly go back. I mean, we're pretty much done. I'm supposed to tell you guys that lunch is from now until 1. And that we come back and it's in the same rooms. There's one here and another one in the same place that it was before. I don't know where that is. And I don't know who's speaking. Well, actually, I think Sibra maybe is here and Raul is there, but I could be wrong. Check the program. But before I let you guys go, I just want to show you kind of what I did not show earlier. So we did the parcellations. Wait. Here's the comparison. Bingo. So Neuromap stats compare images. This is a function that I didn't show you guys. It is really powerful. You know already how to do everything in compare images by yourself. But what it does is that it can take two maps. This is cortical thickness and mu opioid. I put them in the same space. So cortical thickness is an FSLR. I changed mu opioid receptor to FSLR space. It used to be in MNI 152. You know how to make that transformation. I give it the rotation. Okay, so here's the pro tip. When you make your nulls, the way I made it here is that I took my data and I spun it a bunch of times, and now I have my spun versions of my data. But I highly, highly recommend don't give it data. Just say data is none. And what it's going to return to you is the indices needed for spinning. And those indices you can reuse. You don't have to remake spun data every time you want to do a correlation. You can just get the indices, do it once, it's going to make your analysis way faster, and then every time you want to do a comparison, just use your indices to make a new map. Does this make sense? You guys know what I'm talking about? I got no nods. Probably means does not make sense. I'm getting a one nod. Okay, so essentially, it takes a while to spin stuff, right? Because you're projecting it to the sphere, spinning it on the sphere. Now, instead of doing that for every single data map that you want to make a comparison with, just do it once, get the indices. So like if you have your map and you say, oh, brain region 1 needs to now get spun to brain region 10, and brain region 2 needs to go to 25, and et cetera. You only need to do it once. You can reuse that every time you want to do a spin test, which is the permutation test that I just described with the spatial null. Okay? So data equals none, that makes your life much easier. That's usually what I do. You can do it in the specific space and density that you want. And then with that, using compare images, you give it the two data maps in the same space that you want to compare. You give it the nulls, and it's going to spit out correlation coefficient and spin tested p-value. So you don't have to do the whole permutation test yourself. I mean, you could. I usually do, actually, honestly. But this is like just the fast way of doing it. Okay, it's 12:01, so I'll let you guys go. If you have questions, feel free to ask me or Vince. Yeah, what's up?
So you asked question should go first. I have one little comment to
Yeah.
touch on from earlier. It's okay. Somebody had asked if you had a transformation to BigBrain space and you kind of deferred them to BigBrain Warp, saying that's already been done. You know, they would have a nice tool. But I wanted to gently clarify that BigBrain Warp is actually a wrapper, and it has surface-based transformations actually from our group. I have an MSM registration. And there's also a volume-based transformation from another group. Anyway, so if you're interested in incorporating it in here, we'd be happy to have that.
Yeah,
the
nice.
goal is just to have it more easily accessible for everybody. And
Yeah.
I'm going to give a talk on actually our newer version of our registration tomorrow.
Nice.
So
What's it called? Like, how do I find it?
if you actually go back to the BigBrain Work page,
Yeah.
at the bottom it says how to cite. On the bottom left,
Oh, sorry, yeah.
how to cite. And yeah, at the bottom, Lewis, that's our group.
Okay.
Space, and above it is volume-based. But anyway, the one that they have in the wrapper is a few years old, so
Okay.
I'm going to give an update on our new one tomorrow.
Nice.
So just so you know.
Nice. That's awesome. Yeah, great.
Okay.
There we go. So if you want, yeah, going from BigBrain to others, and yeah, we should integrate it. So I will be in touch. Yeah. All right. Nice. Yeah.
Super quick question. So if you have a brain map that you want to compare with all these other maps in the library, is there a statistical correction for the number of comparisons of maps? So, I mean, you went over the spin tester within a map. If you went on to, correlate your map with, say, 10, 20 other
Yeah.
things, how would you advise people to proceed?
Yeah, I would definitely multiple comparisons test. So that's what I did in the example I show, or in general if I'm doing these massive things. Or I would advise that you go in with some sort of hypothesis and a bit of more of a narrow focus. Like, yes, like there's a bunch of data out there, and yes, you could do a massive core, but it can be really hard to interpret when you have 78 maps and you're like, okay, now what do I do with that? And it's kind of, I mean, sure, you can do it with big data, et cetera, but yeah, so definitely multiple comparisons, but also a good idea to focus in on, I'm interested in metabolism and stick on that route. Yeah.